Bharti with Abhilash Sarkar. In this chapter, I will continue on the fluid dynamics, the part of the another flow that we have already already described. That there are three kind of flow. Out of that, steady flow we have already described. This time this is turbulent flow. Now, if you can see the pattern of a flow in a river or any canal, you can see that that is not very much uniform flow. It's a very disordered flow. Why? Because that is being always being disturbed by the edges of the river, and it is being directed different directions after hitting the edges. Okay, so and that too, the first of the kind which is distinguishing it from the steady flow is that the flow is high. In case of steady flow, that we have taken in consideration where the flow is very less low, the steady flow will exist or level of flow will exist. But in this case, the flow is by its nature is very high, and restriction due to the edges, it will be diverted different. So due to that, what happens if say that this is the path of the river. Now in between there may be a streamline flow, but the flow which is adhering to the edges and being hit, and it will cross other streamline. So there this is not the condition of a steady flow. Steady flow, no streamline will pass through. So you will get this kind of flow in the river and canal, because that is not very much ordered or uniform flow. Okay, so these are the two things that will turn a steady flow practically into the turbulence flow. So we can say the most of the flows we can see practically are turbulent flow, not the steady flow. So this is the idea of a turbulence flow. Turbulence flow, not much I will move on this, because that is a different subject and then it's not covered in the lower class. So that I will not talk about. Now, one more distinguish the number, that is the Reynolds number, which is a dimension due to which we can at least make a boundary between the steady flow, unsteady flow, and turbulent flow. What are these? The Reynolds number is being calculated by rho Vd by eta. Now, what are those parameters? Let's say this is a pipe through which the flow is moving. Okay, so now this is the diameter of the flow path. Okay, v is the velocity of flow as a whole. This is the as a whole, because we know the velocity may also differ, that I will discuss. So velocity, but this is the velocity of flow, and eta is the viscosity. Eta is the viscosity of the fluid flowing inside. So that I will also discuss later. And rho is the density of the fluid. So all together, this will be a Reynolds number. The beauty of it is a dimensionless number. So that means you won't get any dimension, only you will get some number. So with that number, how will you decide which flow is what? So first thing is that if Reynolds number is less than 1000, then you can definitely say it is a steady flow. Okay, so below 1000, any number, it is, so that is being derived by so many of experiment and practical results. So from that, it has decided that below the 1000, if I get the Reynolds number value, then it is a steady flow. Second trigger is the Reynolds number is value is above 2000, then it is turbulent flow. There is no exist of steady flow or any flow further. It will be converted in between 1000 is a patch of Reynolds number which will be a different kind of flow, that is unsteady flow, that I have already explained with the example that where that unsteady flow will, in unsteady flow that the velocity for steady flow is uniform and uniformly changed in between two same gap, the change in the velocity or the velocity will be same. Okay, but in this case in between two similar gap through the flow, the reduction, the change in velocity or the velocity is not uniform. So that is the pattern of unsteady flow. So this is the condition. Now prior to moving into the details of this, I have to discuss another thing, that is that already I have taken a help during discussion of my theory in fluid dynamics, that is when there is a steady flow. In case of steady flow, what is constant? The mass flow rate is constant. So from that, what we can derive, if I can say that mass flow rate constant, so in case of any non-uniform the flow path where the cross section is changing, we can say the mass flow rate at point, let's say 1, and mass flow rate at point 2 are same. So how it would be? So if it is mass flow rate at 1 is equal to mass flow rate at 2 is same. So mass flow rate is nothing but what the volume flow rate at 1 into volume flow rate into density at 1, volume flow rate at 2 with its density will be same. So densities will not change because this is, we are assuming it incompressible fluid. This is the assumption. In case that density changes due to some reason, so that has to be considered. That will be rho 1 and rho 2. That will be, but our discussion we are talking about ideal fluid, so this is incompressible. So that case rho will not change. So if rho is not change, velocity is the volume flow rate is what? Volume flow rate is nothing but the cross section into the velocity. So how come that velocity is there? Because velocity is nothing but distance per time. So that means if I consider for 1 second, if time is equal to 1 second, then the velocity is equal to distance. So distance traversed into the cross section will be the volume inside this in 1 second. That much of mass is going cross section, means volume, and density if you multiply that will get cut. So ultimately the volume flow rate has to be same for steady flow. Mass flow rate we understand, because this incompressible there is no chance of retention of mass. So whatever mass is passing through one segment, it will be passed to the other segment automatically, as because there is no chance of retention and fluid is incompressible. So from there we can see that this is converted into volume flow rate also same. So mass flow rate is same, volume flow rate same for steady flow, and in turn the cross section into the velocity is distance. So cross section of this into the velocity, that means the distance traversed within this, that is some mass or volume is accumulating. This volume will transfer to this when it is passing through this cross section. Okay, so the cross section into the velocity of this part will be the same. So this is nothing but A1 A2 is equal to A1 V1 is equal to A2 V2. Understand? So that means this we can say is constant. So now if this is constant, that means overall cross section into velocity at any point is constant. Okay, so now if it is so, we can say that velocity at any point is inversely proportional to cross section for steady flow. So for steady flow, if the cross section reduce, velocity will increase, so we will get a higher velocity here, that we have already described during discussion, where the crowdness will increase, your velocity will increase. So there's a crowdness is increasing and velocity that is also can be proved by this mass flow rate this way also. Okay, so this is the part. Now we will come back to the part we are discussing here. One thing is very much unknown for us, it is the viscosity. Now what is viscosity? Okay, so viscosity, if I define, it is the stress upon strain rate. So what is stress? Stress is just like pressure. What is that? The force, if I talk about the stress, is the force upon area. Now we will come to this. Before that, physically we understand the viscosity. To understand viscosity, if I take example of a slant surface which is hinged air, okay, along the ground, okay, and I am putting some fluid, let's say the water drop we are putting. So you can see the movement of this water along this surface. It will be can be observed. Now instead of water, if I change into honey, let's say honey basically we can see physically it is more thicker, it is not flowing very fast. So if I put honey, it will flow very slowly. So that means what is the property between these two? It is governing that activity, that physical change. When it is water, it is flowing fast, and it is honey, it is flowing less. The property which is governing this incident, it is called the viscosity. So that means more the viscosity, lesser will be the flow rate. Okay, more the viscosity, lesser will be the flow rate. And you can see when it is flowing for water, very less amount of water is will stick to the surface of this. But whereas if we see the honey, you will get more honey is stick to the surface. So we can conclude so many things. If more viscosity, less flow will happen. Now when it is less flow, that means it is a steady flow. Okay, so for high viscosity, we'll get less flow, we'll get more steady flow. Whereas less viscosity, the just contrary, less viscosity, high flow, chances of getting turbulence is more. So water, if it is not the viscosity won't change, so viscosity is set, so there is a chance of getting more flow for water. So if you follow this equation of Reynolds number, this is in denominator, viscosity. If viscosity is more, Reynolds number will be less. Less the Reynolds number, we know if it is less than 1000, it is steady flow. So chances of getting steady flow when this is more is more. So for thicker or the more viscous fluid, the flow is steady flow always. Okay, by this equation we can understand. That is derived with that concept, but I am taking the reverse path. Once if it is true, then this will say that if the viscosity is more, Reynolds number is less, your flow will be a steady flow. Okay, so more the viscous, so we can understand this in other way also, because what do we know that for lamellar flow, the flow is in layer. So one layer is slipping on the other layer. Now the most viscous means the resistance due to friction between layer is more. Okay, the resistance when it is flow on top of another, the in between the friction is more, so the resistance is more, so flow will be less. So the viscosity will increase the resistance of flow, and this because the flow become very less, very slow, and it is become steady. Okay, so these are all connected. So now the viscosity, what I said, viscosity is nothing but stress upon strain rate. So now how you will understand this? If I take a small element in this, okay, so there may be some changes from the boundary. If I say this is y and this is another change delta y dy, and because these are instantaneous changes I'm talking about. Now this layer of this element having velocity v, more you go up, because resistance is here is more, the liquid which is in contact with the solid surface will be less, more resistance will be there, and their velocity will be less. More you move into the center, you will get more velocity. So velocity here can be derived, can be taken as somewhat more. For this infinitesimal distance, we will get dv more, and due to that, this layer after some time, if say this is the t time, after t plus dt, some time later after dt, it could deform like this. This will not be same, because this is faster layer, this will move, and let's say this is dx, this dimension along this is x, so dx is moved, and the angle it is formed is d phi. So stress is the force applied, force between the layer, between these two layers, the force is F and the cross section is A, okay, and the strain is change in dimension. Change in dimension, that means strain means this d phi, angular strain, that means change in position. Strain is nothing but the change from this position, this is forming it. So d phi by dt, in time t it is happening, this is the strain rate. Now this can also be said like d phi is what? D phi means, if I take this separately, this is somewhat straight, but this can be applied because this is very finitesimal. This is dx, this is dy, this is d theta. So s is equal to r theta. S means your arc length is equal to r means dy into d phi. Okay, so d phi can be taken as dx by dy. Okay, so if it is so, d phi is equal to, I am taking dx by dy, dx by dy, and further into dt. Now dx by dt in this side, if I take this dx by dt, that means change in x with, what is this? This is nothing but the linear velocity dv. The dv is changing between these two layers, so this is dv. So if I replace it here, so this will become f by a divided by dx by dt is dv by dy. Okay, understood? So ultimately this is f means f by a is nothing but pressure divided by the divided by dv by dy. Change in velocity with the change in, this is gradient of velocity with the diameter. Okay, so this is somewhat, y means if it is a circular one, you can take it as diameter. If it is flat one, you can take distance. So accordingly, so this eta is nothing but this one. Now okay, now we'll talk about something, why this Reynolds number is unitless. So we'll see the units of all the thing. Now before than that I have to take the unit of this. So now if it is force per area, so force is nothing but what? The mass into acceleration. So force is, we take mass into acceleration, and area is again length square, so it will be L to the power 2. Below it is what we have got, ultimately it is dV by dy. So V is equal to nothing but L by T. So L T to the power minus 1, that is the velocity is length by time, and y is again time length minus, this is the length minus, this is below, so this there it will come L to the power minus 1. Y is the distance, so distance is length, so ultimately this is cancelled. Now this will convert into m L, L will be cancelled, L to the power minus 1, and T to the power minus 1 ultimately. So this can be said that this viscosity is mass is in, if I take SI kg upon meter length second. Now this kind of this unit can be turned into somewhat which is very known, you can say unit kg. If I multiply with meter, and meter square will come here into second, or second square if I multiply, there will be second, another second will come. So why I am doing this? This is a known unit. What is that? Newton. So Newton into second per meter square. So that means it is Newton second per meter square could be another unit of this. Otherwise, if you want to remember, this is kg meter per second. This also be the unit of that. Okay. So Newton per meter square is again, what is that? Pascal. So Pascal second would be the another unit for viscosity. Now coming to this equation, if I put the units, so I will take the simplest solved unit, that is for viscosity it is m L to the power minus 1 T to the power minus 1, and rest of the thing you know. This is density. Density is mass upon volume Q. So mass L to the power minus 3. V is your velocity. Velocity is length upon time. D is the diameter, is length. Now below this is m L to the power minus 1 T to the power minus 1. Let's see where we are standing. M is cancelled, L minus 1 L L, so all these three together will be L cube. If I go up, it will be L cube. Okay, and this T already, and L cube cancelled. So that means there is m to the power 0, L to the power 0, T to the power 0. So there is no unit for this Reynolds number, that can be proved. Okay, so this is intentionally I did because there will be confusion always how come it is unitless, and basically viscosity can be said in this basic unit, but that basic unit is not can be converted into so much of known units, though that I also shown. Okay, so in this chapter I will end up here. In the next chapter I will move on to some more related equation that will be useful for solving mathematics or the problems regarding viscosity. So I will end up here. So thank you for now.